Hi, everyone. Pleasure to be with you all this afternoon. Welcome back to the 6th Annual Water Finance Conference. Andrew Farr here, Managing Editor of Water Finance and Management. We are the producers and organizers of the annual Water Finance Conference. I'm going to go ahead and just get started in just a minute here. I want to go through a few housekeeping items. First, I just want to acknowledge again our main event sponsors this year, the National Association of Clean Water Agencies and Scenario. I know we heard from representatives from both of those companies and organizations on Tuesday. And if you were with us on Tuesday for session 1, I hope that you were able to get something out of it and enjoyed it. We focused on a little bit on short and long-term financial planning, rate setting, and we had a great panel discussion on affordability. So welcome back if you joined us on Tuesday. If not, if you're just joining us for today's session, we're happy to have you with us. We're certainly going to take a slightly different direction with our topic area today. And it was something that we mentioned a little bit on Tuesday. When we're planning for this water finance conference, there's so many different topic areas that we like to cover that kind of fall under the overarching umbrella of financing. And one thing that we discussed a lot with our program committee was to have a session that presented some points on technology implementation and data intelligence in the water utility sector, and how a lot of that factors into cost savings, future financial planning. Like I said, we got into a little bit of that on Tuesday, but we're going to get in depth with that a little bit more today. I do want to recognize our session sponsor for today, Mueller. Mueller has been supportive of the Water Finance Conference since we launched it in 2015. Of course, a lot of us know Mueller. They're certainly one of the oldest waterworks manufacturing companies in the United States. So it's been great to have their support over the years with this conference. I do want to mention to all of our attendees on with us this afternoon, we encourage you to submit questions throughout. You can do that through the chat. You can do that throughout. I encourage you to do that with our first presenter and with our panel discussion later on. We'll get to as many questions as we can. We also had a couple questions on Tuesday about seeing the PowerPoint slides for our opening presentation. Of course, the format for these sessions, we have a half-hour opening kickoff presentation followed by a 90-minute panel discussion. You can see PowerPoint slides. If you're having trouble seeing them, you're going to have to minimize the green window on your left-hand side. And then you will also have to click on the Hide All Sessions button that you should see on the top left. And that should give you a view of the PowerPoint slides and the video feed of our presenters. So we had a couple people asking about that. We also put those instructions in the chat if you're having trouble with that. Of course, you can also maximize the PowerPoint slides to get a better view of those. But if anyone has any questions on any of that, just throw it in the presenter chat and we'll address any questions as we get started here. So without further delay, I'd like to introduce our speaker today, David Hughes, who is going to give our kickoff presentation. David Hughes currently works as an independent water innovation specialist. He previously served as water research manager for American Water. He currently works with innovation companies in the water industry to align them with utilities interested in using advanced technologies to address water system issues. He continues to pursue research in areas of distribution system monitoring, leakage control, infrastructure management, metering, and staff training. So Dave certainly has a wide range of expertise when we're talking about water distribution. So Dave, glad to have you with us. Whenever you're ready, go ahead and take it away.
Okay, thank you, Andrew. And I do want to thank my co-author, Jim Fitchett of Voda AI. And it is an interesting topic. And by now, I suspect most of you have heard about the use of AI in the water industry, in this case, to predict mains that are going to break and trying to predict what mains will fail. Previous presentations that I've done on this subject have explained the process and provided the case studies to document the success, really some stunning success of this effort. But since this is a finance conference, I thought I'd shift gears a little bit and take a look at the value, the economic value of employing this technique. Up to now, it's largely been just left up to the imagination of the utilities to picture what it would be like to know exactly, or pretty close to exactly, what mains are going to break in the next year, 3 years, 5 years, and so forth. And utilities do know the costs related to main breaks, the direct costs of loss of finished water, repaired cost, and damage, and the indirect costs, which include interruption of traffic and commerce and damage to utilities' reputation. Today, many utilities are also investing in finding leaks to minimize break impacts with various leak survey methodologies. Water utilities must also replace aging infrastructure to reduce those breaks. So capital investments are made to not only investigate the buried assets to see if they're ready to be replaced, but also to make the replacement itself. So to improve the timing of replacement, many utilities do work fairly hard to try to figure out just exactly which pipes are weak and are soon to break. Main break history has been a major clue to this analysis, and the analysis has been expanded to look at similar pipes, cohort pipes, so they can actually focus on particular types of pipes that are most likely to fail. Utilities can choose from an array of contributing break factors and weigh them to prioritize pipes for renewal. There are also utilities that invest in a number of asset management techniques to directly look at the physical condition of the pipe. The risk of pipe failure includes an understanding of the consequence of failure, as well as the risk of failure, or rather the probability of failure, and aided by hydraulic modeling, have been able to focus on consequence to reduce the more catastrophic types of failures. These main break techniques have really not been totally successful, and some far from it, trying to determine what buried pipe will fail given the differences in the pipe characteristics, the pipe environment, how they were installed, and so forth. And then weighing these techniques in a proper fashion is really a very complex issue. So this is where machine learning comes in. Machine learning has the ability to sift through virtually unlimited amounts of data and find elements associated with events like main breaks. The graphic in this slide, up there in that upper right-hand corner, illustrates an important concept that main breaks are not caused by a single combination of factors, but by multiple combinations of factors. These combinations can vary significantly. Understanding these combinations could also prove enlightening to operators down the road, but also consider the significant value identifying pipes with a low likelihood of failure and those that are not going to fail in the very near future. So allow me to step back here and just briefly go through the machine learning process. This is basically the VODA approach, but it's really left to the utilities to look at the similarities and differences between, I guess there are 4 companies now that do this machine learning process. The first requirement, of course, is data, accurate data. The process then includes checking on that data to make sure that it's properly assembled and gives you good information on which the machine can base its decision making. And then, of course, the algorithm itself that analyzes past breaks in order to predict what pipes are then likely to fail in the more immediate future. And then finally, there's an output component to this, where either graphically or in a tabular form, the information is provided to allow analysis and understanding which pipes are going to break first. So that first step, collecting data, I basically categorized 3 different types of data that are under study. There's utility data, a lot of it harbored in a GIS format, but also, and very key, is good leak or break history, usually in repairs that summarize the pipe types and so forth. There's also regional public data, and this is really varies quite widely. It's environment, it's looking at soils, and some of the ML machine learning companies actually use satellite data to as an additional factor to try to get more precise with what's going on in the background. There's also a third category called proprietary interactional variables, which is a vague way of saying, yeah, there's some things that over time already machine learning companies have found seem to be contributing to some breaks and are looked at. And one actually that VODA has discovered is the slope of the pipe. For some reason, if the pipe is pitched more severely than level, there's some added value or added likelihood of failure. And then comes the reviewing of the data. And in some of these cases, quite simply, the data isn't correct. Some of the vendors will use algorithms to try to spot the data errors in amongst all of the collected data. There are obviously some highly variable things. We all know that weather can play a role in the number of breaks that occur. And one issue that I came across was one of timing, and the example there is the use of operating valves and hydrants. And you need to know when that takes place. If it takes place before the actual break, then it can be a contributing factor. If it happens afterwards, it's probably just part of the repair process. And then we go to the presentation of the data. And as the data is generated, and I'll show some illustrations here of how that's done. But the key thing here is that we're not looking just at the probability of failure, but we're also looking at the probability or the consequence of failure and then the risk. Here's an example of a graphic and tabular display, and I know you can't really read that results there on the left-hand side, but it's basically a ranking of the top 3% of pipes in order of probability of failure, the highest to low going forward. And it's shown there graphically, so you can obviously see if there are concentrations of piping that have a high likelihood of failure. You can also, in most of these softwares, zoom in, use Google Maps or some equivalent in order to see up close what a particular pipe is, and maybe even get an idea of the consequence of failure. And that's what this is. The consequence of failure can actually be derived by the utility using some other independent software, or they can work with the vendor to actually evaluate what pipes have the most consequence of failing. A lot of these pipes don't really have a severe consequence, but you're probably familiar, utility people are probably familiar with those that have high consequence, the ones under roads or in creeks, or large pipes that are prone to cause major flooding or other types of damage, and so forth. And this is all combined to give you a risk of failure. And again, taking the consequence and factoring in the probability gives you a good sense of which pipes might get the guy in the utility fired if they break, and they can actually concentrate and focus on these particular pipes in terms of either replacement or even mitigation. it's clear that not all of these pipes can be replaced immediately, but certainly the operators can go out and make sure that valves nearby are operating properly, that they're doing their very best to anticipate breaks that seem likely to take place. So now let me jump back and let's talk economics. And I wanted to focus on this in two ways. And it has to do with the fact that the utility, without the machine learning, may pick the wrong pipe to replace, thinking it's likely to break, but it doesn't, and actually might last for many more years without failing. And on the other hand, the machine learning might help you pick the right pipe, the pipe that's about to break. So I want to do the analysis essentially looking at what happens if the machine learning aids the utility in picking the right pipe as opposed to the wrong pipe. So I basically arbitrarily picked a utility with 250 miles of pipe. This could also be a study area. It doesn't have to be the whole system, but that's the pretty nominal area. They have about 75 main breaks a year in those 250 miles. And this particular utility is doing a fairly decent job of replacing pipe annually. But roughly 3/4 of the pipes that they're replacing are actually done for the specific issue of main breaks as opposed to other things like water quality or hydraulic considerations, which are also good reasons for pipe replacement. But boiling it down, we're looking essentially at 20 decisions of pipes to replace, and at a cost of $1.6 million. The costs of repairs, as you know, vary, but we'll assume an average here as this discussion goes forward. So what happens when we pick the wrong pipe? Well, if you pick the wrong pipe, not much actually happens other than you've spent money, and we've calculated that at $80,000 for a 400-foot pipe segment. And we've missed an opportunity to actually replace a pipe that will break. So if we had actually paid attention to machine learning and not made that replacement, we would have actually at least delayed the output of cash to replace this pipe by 5 years. And I basically took an interest rate calculation of not spending that $80,000 for 5 years, and just owing to all the conditions that are going on with interest rates and the pandemic and so forth, I'm actually going to provide you a range, if you will, showing a wide variety of interest. So if the pipe is left in place for 5 years and doesn't break, you're actually in better shape than you were as if you had replaced it, because now you've got a pipe in the ground that's already depreciated 5 years without any real changes. So what happens if you pick the right pipe? Well, picking the right pipe, at least you know you're going to have one main break that you've been able to avoid, and presumably in the very first year of the very next year is when this pipe is going to fail. So the focus here is on the money that you've avoided paying out in terms of the repair. So here's a real quick calculation of picking the right pipe. It comes up to about $4,500, but I basically rounded it up to $5,000 for a very simple reason, and that is that we're also looking in most of these cases at the risk of failure. And so it's most likely that the third-party damages or the repairs or maybe the loss of water, some factor is actually higher than maybe your typical. So allow me to round up here to a $5,000 figure that we would avoid if we use the machine learning. So putting this all together and remembering that the utility is replacing about 25, 26 pipe segments and 20 for breaks, we're also looking at 75 breaks per year. So picking one of these at least eliminates one break per year. And of course, then there's the financial consideration of picking the wrong pipe. which varies with those variable interest rates between 8,000 and 38,000 roughly for the unnecessary immediate investment that you've made in replacing a pipe that really didn't have to be replaced. And picking the right pipe in its place, it saved you $5,000 right off the top. And there's obviously some potential for that pipe to break again in another, say, 5-year time frame that I'm looking at. But just assuming one break, the totals run at least $13,000, up to $42,000 if you take the high end of my interest rates. So now you're probably wondering, well, how do you know that the machine learning is going to do that much better than the conventional way of looking at pipes? And I went to a VODA case study of one of their clients where they actually had the utility kind of guesstimate which pipes in advance were going to fail and sort of rank them. And you can see the distribution there on the left-hand side. It's pretty even all the way up and down the area. And there's probably a good reason for that. 36 of those 70 pipes that broke were actually first-time breaks on those particular pipe segments. VODA's probability prediction, on the other hand, actually categorized almost half of these as the highest ranked pipes in terms of likely to fail. So we may be looking not just at maybe one right pipe over a wrong pipe, but multiple decisions that are made correctly. And so now the question is, in this particular example, how many might we assume that would be? It's a good question, but the estimate that we came up with was picking maybe 10 pipes, at least 6 pipes seems to be a realistic number. And I've also included in this calculation, I've actually set an economic level at 5%, sort of the mid-range of those interest rates that I gave you, just to give you a little bit of feedback. And if it involved 10 pipes, we're talking here a net of $320,000 of value in making these decisions. Even if it was half of that, it'd be $160,000, which is well in excess of what the machine learning company would charge you for this exercise. And I would be remiss if I didn't talk about some of the hidden values of this process. First of all, we've talked about data cleansing, that the GIS data would be upgraded and presumably upgraded for other applications that the utility would have. I've only talked really about the savings addressed in year one. There could be some additional savings going forward in continuing the process, as well as identifying pipes that might break more than once in that 5-year time frame that I was looking at. The focus on consequence of failure, if that's not been employed in the past, might also increase the savings by avoiding some of the major damages. And obviously there's a potential, as I mentioned, to mitigate damage by being better prepared for pipes that you know have a high likelihood of failure that are not replaced. But AI does continue to learn and does improve performance over time. That's one of the good parts about this, is that even if it got something wrong in that first year, the machine learns. It gets smarter as time goes on. And then finally, as an engineer, I appreciate the fact that I can look and say, well, why were these particular pipes selected for breaking? And it might improve my knowledge, eliminate some of my biases as to why pipes break. So in conclusion, machine learning, and there are examples, and the good news is that utilities can go out and do this themselves. They can hire the machine learning vendor and have them do a trial. And the way this is set up is that you don't tell the company what pipes have broken in the most recent year, and you give them the previous year's histories, and they try to project and predict what pipes have broken in the most recent year, just to validate the process. the and then finally, at the end here, we have that again, that appreciation for making the right choices and being more confident in making those. And with that, Andrew, I think I'm done and have some time for questions.
Yeah, absolutely, Dave. Great presentation. Thanks very much. Yeah, a couple questions. I think maybe might help us to recap a couple of points. I'm going to go back to kind of the title of the title that we came up with for your presentation, essentially machine learning, data intelligence, and the impact on capital planning decisions. A lot of our audience members on with us throughout this conference are folks involved in financial planning for utilities, CFOs, people in those types of categories. Talk a little bit about, how machine learning or, calculating probability of failure and a lot of the things that you're talking about, how does that impact their position? And how are they then taking all of this information and applying it to kind of future financial planning?
Well, yeah, I guess the biggest thing that utilities are pressed to do is to perform for their customers, and nothing like catastrophic breaks or just repeated breaks have the potential to annoy a customer more than that. Maybe some water quality issues potentially, but from my perspective, I would say that being able to perform better, and I know from my experience at American Water, they said, well, we increased how many mains we replaced, but our main breaks are still increasing, and our water loss is still going up. And part of that has to do with making the wrong choices, that there was evidence that was going on top of the fact that the infrastructure is aging rapidly and breaks will increase, I'm afraid, for a few years to come. So this becomes a really important criteria and definitely attracts the customer's attention, who ultimately may be participating in just how much money you will have for capital improvements. I've seen places where breaks are so severe, and rather than have a public utility commission allow them to get more money, they restrict the money because they're saying you're not using the money wisely, so why should we have our customers give you more money? If you can demonstrate that you're improving the statistics, you're lowering the water loss, you're lowering the number of breaks, that would help. And keep in mind, if we had, in my discussion, if we'd avoided 10 breaks per year, that's 10 out of the 75 that we've done just by virtue of the machine learning, let alone the other 10 pipes that were also replaced from that list.
Yeah, we're talking a little bit about water main breaks and all of this. In the last week or two, I think an ASCE report that they did, I think with some other associations involved, came out, and they were talking about just the underinvestment in the overall water sector. And there was a stat mentioned in there, and I don't think it was anything new. It probably was taken from some other recent research, but I think it was something like, since 2012, just up until now, water main breaks are increasing significantly. I think maybe like a 28% or something to that effect increase just in the last 8 years or so. I mean, I wonder, just based on your experience, what do you make of that? Is that just simply aging infrastructure like we always talk about? Is there something that utilities could be doing better on the management side? I just kind of wonder what you make of that.
Well, yeah, it is the aging infrastructure, and there have been a number of studies talking about the perfect storm of pipes from the 1880s that are, some of which are still in the ground, finally beginning to break, while some of the less structurally sound pipes of more recent times, because they're thinner and more prone to corrosion, might also be breaking, and a category like asbestos cement pipes are also beginning to break. So we're looking at multiple types of pipes that are likely to fail all at the same time. So we've got to make really good choices, and that's why that consequence of failure component is important to at least minimize the damage. It's important from this machine learning perspective to actually be able to predict which mains are going to break, so that you can, even if you can't replace all of those pipes, you might be able to maybe valve them down, or at least know that the valves aren't buried under a recent paving project. And you can also be smart going forward, because if you know what it is that's causing these breaks, the pipes that you're installing today can be designed to overcome whatever those issues are.
Yeah, final question, Dave. I want to ask you about machine learning. Obviously, it's been something that we've talked about a little bit so far. I'm wondering
Can you hear me?
Yeah, Dave, I've got you. Can you hear me?
Sorry, I've lost transmission.
Ooh. Can you hear me okay, Dave? I can still hear you. All right, everyone. Well, we seem to have lost Dave here, but we were wrapping up anyway. So with that, we'll go ahead and conclude this presentation portion, but we will see you all in just a minute or so. We will get started with our panel. We'll actually get Dave back on the panel discussion, so we'll get some more perspective from him here in just a minute. So everyone, we'll see you soon.